This will be section 3.6 in our Math 121 course. It is on variation. It's a fairly quick and easy to do section. It is great for building formulas, and it's used in the sciences a lot, so we'll think about it from the perspective of the sciences and how variation is used. Variation is just what it says. How does one thing vary as you change something else? So we'll list some formulas first. First we have direct variation. And in that case, we're just going to say something like force is proportional to acceleration. It directly varies as acceleration, so we could say it's equal to within a constant, and it turns out the constant is mass. So we can get rid of proportional signs and just put in an equal sign. And the important thing about direct variation is if I were to double the acceleration, I would double the force. Or said another way, double the force, you'll double the acceleration. And I think you can see that. Just multiply by 2. 2 times the force equals mass times 2 times acceleration. So it's directly varying. Then inverse variation. And that's going to be something like pressure is proportional to a constant divided by volume. So in this case, if I were to double the volume, I'll cut the pressure in half. So pressure, I shouldn't have an equal sign here because I have put the constant in. I'm going to put an equal sign right there. That is a constant. And in this case, again, I'm going to double the volume, so twice the volume, and that cuts the pressure in half. Of course, I could do direct variation in another form, such as a power. For instance, I have force could be equal to a constant times velocity squared. That turns out to be wind resistance. If you're going very fast, the force is proportional to the wind speed, but it's proportional to the square of the wind speed when it's going fast. So I could do it as a power, and that would be direct variation as well, only it's direct variation as the nth power. Same way with inverse variation, I could do a case there as well, and in that case I'm thinking of gravity is equal to a constant divided by the distance between objects squared. So there's an inverse squared proportionality, and it comes up quite often. The inverse squared laws, in fact, there's a whole series of them that are called laws just because we know it always works that way in the sciences. So that would be direct variation, inverse variation, either directly as to the power of 1 or a square or cube or some other thing. Here's another one for the inverse back here. The inverse could also be said magnetic field. I guess I use a B for magnetic field. And it's not important. We're just borrowing equations from sciences. That is equal to a constant divided by the distance from the bar magnet cubed. So I could vary as a power, I could vary directly as the power of 1. Then I could have joint variation. And that's where I could have a whole combination. So the gravity is a good one for me again, so I'm going to borrow gravity. So force of gravity is equal to a constant known as the universal constant of gravitation times mass 1 times mass 2 divided by distance between them squared. So here's the joint variation. Gravity depends on the variable of how much mass in number 1, how much mass in number 2, and r squared. So there could be 3 different variables in here and only one constant. So these are all the types of variation I could have, and basically I can do experiments in the lab and investigate if something varies directly, or if it varies inversely, or if it varies as an inverse squared. I can keep probing around and build mathematical formulas that will describe how things behave in the real world. So this turns out to be a great method for determining how laws, mathematical laws that govern our physical world, it's a great way to find them. So what we really want to do in most of this, the biggest chore, is to find constants. If you could find the constant, then you'll have a formula, and it's just a matter of plugging in the formula. So now I want to go to my next page, and that's variation. And here I want to just start doing some examples. So I'll start with the spring. And this actually has a name. It's called Hooke's law. And what Hooke found was that the force from a spring is equal to K times the amount you stretch the spring or compress it. Now technically it was equal to a minus K, but we won't worry too much about the plus and minus sign. So basically what Hooke found is that if he were to take a spring and stretch it, he could get, let's say, 10 pounds. And I'll just make these numbers up for example. I like to put square brackets around the units to make sure they don't get mixed up with variables. And he found that in that spring's case, it was for compressing that spring by 1 inch. So, given that I know this information, I could pretty much plug in find K. So I could do that. I'll just plug in 10 pounds in 1 inch. And that's going to be equal to K, or written in variable form, that's force divided by X is K. So my K in this particular case is 10 pounds per inch. So now that I know what the K is, I can go ahead and find it for anything. So suppose X equals 1.3 inches. Well, find force. That's going to be force equals my K, which I already know to be 10 pounds per inch, times 1.3 inches. Notice that in the units, the inches go away, and I'm left with pounds. So if I stretch that spring by 1.3 inches, I'll get 13 pounds. So a lot of it is just finding the K. If we could just find the K, then we're good. Let's go to another. Or we can just plug in and see how things may vary. So back on Hooke's law, we would find the K. Let's say I have force equals B times V squared. This is wind resistance. And in particular, it's wind resistance when the wind speed is high. Often when the wind speed's low, the formula is F equals B times V without the square on it. But we'll just assume that this is going to be F times B V squared. So in this case, we'll say the force on a billboard, for example, might be, let's say it's 1,000 pounds. And that happens when the wind speed, V, equals about 20 miles per hour. So that's the data I have. If I have that data, how much force do I have if I double the wind speed? So I'll say find force for double the speed, or 40 miles per hour. Now I've got two ways to do this. One is I could plug in the data and find the constant B. Then I would have the formula and I could plug in for any numbers. Or I could just plug in that 2V. So for example, I know, I'll say this is F1 and this is V1. I know what the situation is. F1 equals B times V1 squared. So if I plug in that 20 miles per hour, I know I'm going to get 1,000 pounds. That's what F1 is. So if I now double it, so I'm going to put in twice V1, that will be my F2. So that's going to be B times twice V1 squared. That's the same thing as B times 4V1 squared, since I have to square the 2. And if I write that out, I see that's nothing more than B times V1 squared times 4. And that's going to be 4,000 pounds. So you could say I never really needed to get the B. All I needed to know is how, since I knew it was varying directly as the square, all I needed to do was plug in how many more times my new speed is versus my old speed, and I could bypass that B. I could always go the other way and just find B. And that's always straightforward to do, and you can always back up and do it that way. So I could then say F1 divided by V1 squared, that's going to be my constant B for this situation. In the case of wind speed, it may be temperature and humidity and other factors in there that may change what that B is. So in this case, it would have been 1,000 divided by 400, and the units of this would have been pounds on top and miles per hour squared on the bottom. So I've squared the 20, and that's how I got the 400. So if I divide that out, it looks like it's 10 divided by 4, so B equals 2.5. Then I could rewrite my formula as F equals 2.5 V squared, and now I could plug in any value I wanted for V, and I would get it. So finding the constant is really the key. We'll figure out what the formula is, whether it's a direct variation or varying as the square or varying inversely or jointly varying. Once we know what it's doing, then most of our job is to either find the B, that is the constant of proportionality. Let's go on to something more complicated. Let's go on to a joint variation. And in this case, we'll use gravity. And it's a complicated variation. So the force formula here, I'll put it force sub gravity, so we know it's gravity force we're dealing with. That's going to be G, mass of the first body, mass of the second body, divided by the distance squared. We can put a picture on this one. Here's the mass of the first body. Here's the mass of the second body. And distance squared between them. So now we know what the force is. That's force of gravity pulling one this way, and it's pulling the other with an equal and opposite force the other way. So in this case, I have either a direct variation or an inverse variation, depending on whether or not I'm changing the R or if I'm changing the mass. So let's say I have the mass is going to stay the same, but I'll draw a new picture and I'm going to move them so they're 3 times farther apart. Can I do that? Here's mass number 1. Here's mass number 2. And now my distance, R, is going to be equal to 3 times the first distance. So I'm going to adjust this thing here. Get rid of that square, I don't need that. And just call this R1. So now my R2 is 3 times R1. So the masses haven't changed, but the distance has gotten quite a bit bigger. So now I know what to do. I could either plug in, I'll give mass values here. M2 equals 10 kilograms. M1 equals 10 kilograms. And we keep these masses the same, but we triple the distance between there. Clean that up a little. So I think I can see right away what to do. I know my first force was going to be G M1 M2 divided by the distance R1 squared. My second force is going to be the same quantities, M1, M2, but now I'm going to triple the distance, so I'm going to multiply 3 times R1 and cube all that. Or excuse me, not cube it, square it. My mistake. Square it. So when I do that, I can see I'm going to have GM1, M2 all over R1 squared. That's the old formula. And now I'll square the 3, and that makes it 1 over 9. So this thing right here was the original force, F1. Now that I've moved it, I've dropped it by a factor of almost 10. So, for example, if F1 was equal to 10 newtons, newtons being the unit for force, then F2 would be 10 divided by 9, or about 1.1 newtons. So we can see how it varies. If we see something dropping in this fashion, then we know it's varying as 1 over r squared. If r stayed constant and I made m1 bigger, then it would be directly varying. If m1 and r stayed constant and I changed m2, then it would be varying directly as m2. So in almost all of the examples that we do, what we're really doing is just figuring out how things vary and finding that constant. So again, if